So when we start talking about sets, I've drawn out the sort of blueprint for us, so it'll go a little bit faster. But you'll notice here I have this little one in the middle labeled natural numbers, and the natural numbers are the ones that we always think of. Just 1, 2, 3. Sometimes people call them the counting numbers. And I'm using set notation. This tells us that it is all the positive whole numbers, and these little ellipses tell us that it goes on forever to infinity. The next set is the set of whole numbers, and the set of whole numbers is very similar to the natural numbers. Again, I use set notation to let us know that we're doing a set of numbers, and again the ellipsis telling us that we're going to infinity. So the only difference we see between the natural numbers and the whole numbers is that in the whole numbers we have 0 added to it. You will also notice that the natural numbers are within the whole numbers. So every member of the set of natural numbers is also in the set of whole numbers. The next set that we have, and you'll notice again that this set is including the natural numbers and the whole numbers, is the set of integers. And the set of integers, again, set notation, but what we're including now are the negatives. But again, we've got 0, 1, 2, again to infinity. So we go to infinity to the left, we go to infinity to the right. So we have a pretty large set here. Again, the set of integers is including the whole numbers. It's also including the set of natural numbers. Now we go to the next bigger set, again including the 3 that we've already talked about. And this set is the set of rational numbers. And the set of rational numbers includes everything above, but it also includes other stuff. Now this one I can't show you sort of in set form because there's a lot of things that are included here. If we look at this and we see that rational numbers, so there's ratio in there, that's our root that we want to think about, and the word ratio is telling us that it's going to be anything that can be expressed as a ratio. It's generally considered a rational number. So we include all the stuff above. We can make all of these integers look like a fraction if we want to make them look like a ratio. So we include all that. But the things that we also would have to include would be things like 1/2. Again, we have to look at sort of the variations. So we've got 4/3, 2 and 1/5. So all the different forms of fractions, those are all in there. The next idea that has to be included in here are things like 2.7. These are considered terminating decimals. And we're also going to include 3.333, where that 3 is repeating, and these of course are considered repeating decimals. So again, natural numbers are included within whole numbers are included within integers, and rational numbers include all the stuff that's in integers. So we do want to include all those numbers that we had up above, but we also have to include all these types of numbers that we've just discussed. So the next set is the set of irrational numbers. And the set of irrational numbers is very specific. These include all non-terminating so they don't end. Non-repeating decimals. So let's talk about a few different versions of this, and the one that most of you are probably familiar with is pi, which is, we're talking about this pi, not the pie we eat, which is a decimal that goes on forever and has no pattern, and that is the hallmark of the irrational numbers. Another one is E, and we don't use E in this class. I think the first time you will see E is in, I believe it's college algebra. Different types of numbers that we can also be seen, or that are also seen in this irrational number, are things like the square root of 3. If we were to take the square root of 3 and put it into a calculator, we would get a non-terminating, non-repeating decimal. I'm also going to include a radical like this, but with a negative on the outside, so the square root, or the opposite of the square root of negative 11. That negative outside makes it okay. One of the things to remember here is that you can't express any of these numbers as a quotient or as a ratio, so they cannot be expressed. Now, we did talk about a couple different things here, and we're going to have to come back to that in just a second so I can deal with this. But before I do that, I do want to tie all this stuff together. So I've got the set of rational numbers, this set here, which includes all of these little sets, the subsets. So we've got the set of rational numbers, and then I've got this set of irrational numbers over here. But I need to tie them together. And I tie them together calling them the set of real numbers. Now, the fact that we have to tie this together and call this real numbers always sort of implies that if we have to say that there are real numbers, that implies that there are non-real numbers, and that's what this little sort of oval is expressing, so our non-real numbers. And now we're going to have to take that step backwards when we look at these two radicals. So when we look at, and I'm just going to go down here, let's look at this, and we know that the square root of 4 is, of course, 2. And then we can also do the opposite of the square root of 4, and we know that that's the opposite of 2. And that should make sense to everybody. We know that what we're looking for when we're looking at radicals is the square root of 4 is 2 times 2. So the square root of 4 is 2. So that's 2 and 2. And the same thing happens here, except we had a negative on the outside. Now the key is that this is the same. Now, one of the things that we should note when we look at this, and this is not something that you're going to see in this class, but it is getting you hopefully prepared for the next class. When we look at the square root of 4, we see that we're used to doing this 2 times 2 is 4, so the square root of 4 is 2. And that's not the only number that if I multiply it by itself, it's going to get me 4. I could multiply negative 2 times negative 2. Negative 2 times negative 2 is definitely 4. We're using integer rules here. So this is also negative 2. Now, this is the principal root. When you get to the next class, you're going to see this, and you're going to see it expressed as plus or minus 2. And this is why, because when we're looking at the root, we're looking for a number that when we multiply it by itself is that number. The number has to be the same, and we see that we've got these two numbers. Now, I know this feels like I'm going into a lot of explanation, but it's all going back to this this non-real numbers idea again. Now, we see that when it's got the negative out front, that's okay, because we just bring that negative with us. This is literally just an order of operations problem. So what we have to go to now, what we haven't seen is, what about the square root of -4? Again, think about this and say, what do I have to multiply? What number can I multiply by itself, exactly the same number, that's going to get me -4? And when we think about this, the truth is that integer rules tell us that there is no number that I can multiply that's exactly the same that will get me a -4. Because a positive times a negative is the only way to get a negative. So this cannot be done. And this idea is the principle behind our non-real numbers. If I've got a negative underneath that radical, or a negative radicand, that's where the non-real numbers come from. And some of you might remember this from high school or from a few years back, that when we see that negative underneath, that's where you get that I. So this is actually 2I, and we don't have to do this in this class, remember. I'm just trying to remember where this non-real comes from, because we are going to see this idea a little bit. And they're going to talk a lot about this in the next class. Okay, those are our sets. Now, let's talk about a couple different things that we might encounter. So if, let's say, for example, we ask what number or what sets does this number belong to? So if I put -15, what sets does this number belong to? Well, -15, we know that the first place -15 would be seen, because it's a negative, would be in the set of integers. So it's in the set of integers. But it's also in a set that's bigger than the integers, so that would be the rational numbers, because the rational numbers include integers. And the rational numbers are within the real numbers, so it's also included in the real numbers. If you have a number like 0, what sets does that belong to? Well, we can see that the first place we see 0 is in the whole numbers. And then it's in every set after that. So it's the whole numbers, it's also in the integers, the rational numbers, and of course the real numbers. So what if we chose a number like 2/5? 2/5, again, we look for the smallest set where we find it, and that would be in the rational numbers. That's where we see all the fractions. So that would be the rational numbers. The rational numbers are also included in the real numbers, so this would also be real. If I asked you what set pi was in, and we see that pi is in the irrational numbers. And also, of course, the real numbers. So that's how you would do, if when we ask you what sets do these belong to, this is how you would work any of those.